Now previously we were looking at PV equal to a constant. I had an expression involving P and V. Here I have an expression involving V and T. Can I use this ideal gas law to simplify things so that I get an expression involving P and V again? Well, I see here that T, if I solve this equation for T is equal to PV over NR. So we could substitute that into this expression. So I see that V times PV over NR to the F over 2 is equal to a constant. Now this V times V to the F over 2, this is a V to the 2 over 2 times V to the F over 2. So that looks to me like a V to the F plus 2 times P to the F over 2 is equal to a constant. You might be wondering, what about this NR? Well, I know if I raise NR to the negative F over 2, well, that's a constant as well. So I'm just dividing both sides of an equation here, dividing the constant. This is equal to some other constant, but it's still equal to a constant. What I'm looking for here is a relationship between V and P. So I have this expression here, and I'd like to make it a little bit simpler. Let's take that. And note that I could simplify this whole thing by raising it to the, if I square this, I will clear the 2 in the denominator of the exponent. And if I take the fth root of it, I will clear this f from the numerator, but need to divide by f here. So that shows me that v to the f plus 2 over f, these 2's cancel, f plus 2 over f times p to the f over 2 times 2 over f is 1 times p, therefore, is equal to a constant. Comparing the two results that we got then, I see that for an isothermal process, P times V is equal to a constant. So P is proportional to 1 over V. For an adiabatic process, P times V to the F plus 2 over F is equal to a constant. F plus 2 over F is kind of a mouthful, so we have another name for it. We call it gamma. Gamma is equal to F plus 2 over F. So notice for a monatomic gas, G monatomic, will be 3 plus 2 over 3, 5/3. And for a diatomic gas, who has 5 degrees of freedom, we have 5 plus 2 over 5, so that would be 7/5 or 1.4. So we say P times V to the gamma is constant. And that is the difference between these relationships. So here we're raising V to the 1. In the adiabatic process, we're raising V to a constant that is greater than 1, and that characterizes the relationship between pressure and volume for this faster process that does not allow the flow of heat. Often when we want to know the change in energy of the adiabatic process, because there's no change in, because there's no heat, what we want to know about is the change in temperature. So in those cases, it's simpler often to use the relationship between V and T rather than P and V. And in that case, V times T to the F over 2 is equal to a constant. And thinking about the other things that we can compare in these two processes, the isothermal process is slow. The adiabatic process is fast. These are both idealizations of those ideas, slow and fast. Slow happens so quickly, slow happens so slowly, meaning that there is no change in temperature. Any heat that needs to flow out does, so that there will be no change in temperature. So this means delta T is 0, or T final equals T initial. And in the adiabatic process, the opposite is true. There's no time for heat to flow, so heat is equal to 0. If there's no change in temperature, we know there's no change in the energy of the gas, change in thermal energy, is 0. That's equal to the heat plus the work, which means that the heat in this case is equal to minus the work. Here the heat is 0, which means that the change in energy is equal to just the work. To find this work, we can note that the change in energy in this process via our analysis with the equipartition theorem is equal to F halves number of moles R times the change in temperature. And how do we find that change in temperature? Well, by using this fact here, that the volume initial times T initial to the F over 2 is equal to volume final times T final to the F over 2. Apologies that I have final here and F for degrees of freedom. But given any two volumes and a temperature, we can find the other quantity that we don't know and use that change in temperature resulting to find the work in this process. So that is an overview of isothermal and adiabatic processes and how to calculate the heat and the work in each